We're going to start on a new topic now, and it has to do with an application of plasticity as well as elasticity that has become very fashionable, and one needs to know something about it in order to say they know plasticity. This cover from the book by Ted L. Anderson is the best book I know. There have been a lot of books written about fracture mechanics. Many of them are rather practical in that they are written for industry, but Anderson seems to have a pretty good grasp of the whole business, and he covers some stuff that is very important, and in particular the failure assessment diagram, which is part of a number of codes, particularly codes in the oil industry. They're quite common. So we'll be taking a lot of things out of Anderson's book. Unfortunately, I don't know him, and I don't know much about him. I haven't been able to do anything but determine that everybody knows him or knows of him, but nobody knows anything about him. So that's the way it's going to have to be. Let's going now to the next slide. I've got something here that I prepared some time ago, and it's related to the burst of pipes. There's a lot of burst testing that goes on in the oil industry. That is, you take a pipe that might be, anywhere 5 to 12 inches in diameter with a wall thickness that maybe ends up with a diameter to thickness ratio of maybe 12 to 15 to 20. You pressurize it until it pops, and then you would like to have some kind of a theory to apply to all this this work that you've done to make the measurement. The two equations given on this slide that we're looking at is what most people use either for testing or whatever, or for design. And it's really, going back to some of the plasticity stuff, it's really the limit load, the pressure limit load that you would get for a pipe. There's a slight difference whether you have a closed end or an opened end, because on the closed end you get an axial stress, and of course the hoop stress is an axial stress. So hoop stresses help each other with the von Mises criterion, and the pressure for the closed end cylinder for burst is higher than for the open end. The place where fracture mechanics comes into this is that it's known, and in fact they're measured, it's known that these pipes have flaws in them. They have some ways of trying to measure flaws, usually acoustically. I don't know that at this time that they're able to really do a good job, but they do their best. And for certain kinds of wells, every pipe that goes in the well it is subjected to measuring the flaws in the pipe. So the thing would be then, what do you do if you know what the flaw is? If you're making measurements, you ought to be able to establish some limits on how big the flaws will be. So suppose you do that, then what do you do? Well, if you're going to try to do some kind of analysis, you have to assume something about the orientation of the flaw in the cross-section of the pipe. So normally what you do is you just outright make the assumption that the flaw is perpendicular to the direction of the maximum tensile stress. That's where the stresses at the tip of the flaws will be the highest. So you make a few of these sorts of assumptions about size and orientation. And then there's this whole business of fracture mechanics that's been developed to try to deal with that. And in particular, when you get to the last step that we're going to take, what we do is combine the results of all the stuff about the fractures and the cracks and such, and we combine that with the overall plastic behavior. And what it turns out, of course, is that the flaws don't help you; they hurt you. So you would have to scale down a design based on flaw size, and that's where the failure assessment diagram comes in. So we've got a ways to go to get to it, but that's where we're headed. If we take a look at the next slide about the physical basis for fracture mechanics, well, this story starts out better than it ends. What it starts out is that people were interested in studying fractures, and generally you'd think of fracture as happening in a brittle material, and that's where the original studies started. And this fellow A.A. Griffith was very instrumental in getting this whole thing rolling. And let's see, he died in 1963, I believe, and he was an English mechanical engineer, got his PhD from Liverpool, and got interested in looking at the cracks from the point of view of surface energy. He did his original studies on glass, and there were a couple of reasons for that. First of all, you can draw glass into very thin fibers, and the surface is, when it's just been drawn, the surface is pretty much free of any flaws. If you let the fiber sit there, usually if there's any water in the atmosphere, it causes cracks to grow on the surface of the glass. You don't have to worry about the inside of the glass, because glass is amorphous, the hard way to say that it's not crystalline. So things don't happen on the inside, it's all a surface effect. And Griffith did a series of very revealing experiments concerning breaking glass fibers, waiting until the surface had been exposed to an atmosphere that had H2O in it, and showed pretty conclusively that the weakening that you saw in the fiber was mainly due to the growth of surface cracks. Now, he could get up to about 10% of Young's modulus pulling on it, and some of the so-called solid-state physicists of those days were predicting that was, in fact, the kind of limit that you should see. But then, of course, you know that when you look at something like steel, you're looking at yield points the order of 100 KSI or 100,000 PSI compared to Young's modulus of 30 million. So you can see that there's a big drop, and the flaws in crystalline material like steel come from different sources, and I guess that was why Griffith really wanted to start with something like an amorphous material so you could have a better judgment of what's going on, and also you can degrade the material by exposing the surface to different environments. This result was something that Griffith combined with an elasticity solution. And if you take a body and pull on it, and you just hold it, and for some reason there's a crack in it that grows, the load will go down as the crack grows, which would indicate that the strain energy is lessened. And the notion that everybody uses in fracture mechanics is that the development of new surface takes energy, so that when the drop in the available energy equals a certain amount, then you can have a certain growth in the crack, and it has to do with the area, the new area of the crack as it advances. And what Griffith showed was that this rate of change of elastic energy with respect to the length of the crack goes like this equation 2.1 on this slide, and that's 2 pi sigma infinity is the stress far away from the crack, A is the half length of the crack, and E is Young's modulus. This equation was developed for plane stress, and this plane stress solution has kind of worked its way into things, and it's not always recognized that that's a restriction on the kind of solution that's being used. Anyway, this energy that's required to develop new surface area, that would be the energy per square inch. So what would that be? That would be inch-pounds per inch squared. So it's pounds per inch. Is called gamma here, but I'm going to pull what I did before on you, and that is whatever source I'm using, I'm going to use their notation. So this capital gamma is eventually going to turn into a capital G, but it's the same thing. And this gamma now is considered as a material property. So when you're running around measuring things, you measure gamma, and you just add it on with Young's modulus and all the other stuff that you're measuring, and you pretend that this doesn't change. Of course, like Young's modulus and Poisson's ratio and so on, if you change your environment, such as the temperature, then sure, it can change. Okay. The next person in on this was George R. Irwin, a very important contributor to fracture mechanics. And let's see, he was born in 1907 and he died in 1998. So he was after Griffith, but he really contributed a lot to really adding on to the work of Griffith. Irwin was born in El Paso, Texas, but his family moved to Springfield, Illinois. He ended up going to the University of Illinois. He ended up at the Naval Lab and had a very distinguished career. He so much so that he became a foreign member of the Royal Society of London, which, as you know, is a big deal. One of the things he did is he related this property, gamma, to a property that comes from purely elastic analysis. So far, all we're talking about is cracks in brittle material, and therefore one would think they could get away with an analysis, an elasticity type analysis. So he showed for a crack, there's an expression here, for gamma is 1 minus nu squared, this K1 squared over E. Now, K1 squared comes out of, strictly out of an elasticity solution. And you see, that's the good news, because we can solve elasticity problems. We can evaluate in terms of the load what the K1 would be, and that would give us a means of measuring K1 and thus capital gamma. The next thing, and I'm not sure, but I believe Irwin did this, is to relate then this capital gamma, this energy release rate parameter. You want to relate that to the K. And there's a little derivation given here to accomplish that. And at the end, then you get an expression as numbered page 311 in this next slide that we're on. It gives you the relation between this energy release rate and the K1 and E and Poisson's ratio as well. Of course, they're different for plane stress and plane strain. And that kind of, if you think about this sort of stuff, you're talking about the tip of a crack. You know, the radius of curvature at the tip of a crack is essentially 0. And if you wanted to have a solution, what kind of a solution would you work out? Well, the thickness of any real plate is much greater than the radius of curvature at the tip of the crack. So you would, or let me say, I would always choose to have a plane strain solution. Now, as I mentioned, that early solution was one for plane stress, and that's something we got to keep in mind so we can be critical at the proper moment. Okay, so you know what your parameter is. When it gets to a certain, this gamma gets to a certain number for a particular material with a certain environment, then the crack grows. We know how to get from gamma to this stress intensity factor, this capital K, and now all we need to do is find capital K. And that's promoted a great deal of work, mainly in the form of PhD theses. It was just fertile ground for graduate students to evaluate these things, because you look at an elasticity problem, but you've got to include a singularity, which makes it maybe a little more interesting. The next slide shows the solution, the only real solution that we're going to look at here. And what it is at the top of the page is, it looks like an ellipse. But truth is, it started as just a slit along the x-axis. And now what we've done is we put a pressure on the inside, and that's opened the crack. And let's just for a moment say, well, suppose that pressure was uniform all along the crack. Then what I could do is I could add a tension. This is in an infinite material, of course. You know, it's a two-dimensional infinite material problem. I could, way off at some distance y away from the crack, I could apply a tension and apply that everywhere and remove then the pressure on the inside. So I should come back to that solution that Griffith used. The thing that should tip you off that this isn't a garden variety of elasticity solution is that at the tip of this ellipse, the configuration has undergone a huge strain change, because the boundaries of that ellipse used to all be on the x-axis, and right at the tip now, that's a continuously turning tangent at the tip. It is really an ellipse. That is the elasticity solution. So something drastic has happened, and what's happened that's drastic is that you've got that singularity in the stress there, and that's the K1 business. Now the solution I've got here is a little more complicated, and there's a reason for that. We're going to actually use it in a more complicated way. The pressure distribution along the crack, if we pursue that and make the assumption that it's symmetric about the x-axis, and so as indicated in this equation 312, that P of C is equal to P of minus C, then you can write a solution to that problem. And this is something that was really kicked off, in my mind at least, by the Russians. And there was a famous fellow, Mushkilasvili, who championed using complex variable theory to solve problems like this. And this 313 is sort of innocent looking. It's an expression for the K1 in terms of this pressure that varies along the crack but is subject to the symmetry condition 312. The crack opening, and you can see the picture at the top, W is the half opening of the crack. You've got a pretty unusual mathematical expression. You've got the absolute value of a logarithm with all kinds of stuff in it. And this is the kind of thing that the complex variable theory can do for you. This particular solution was given to me by Viktor Dunievsky, a Russian, a very gifted elastician who is in this country, recently retired from Shell Oil Company. So I next point out that when this P of C is constant, then I go back to the Griffith solution, and this K1 is P0 square root of pi A. That's practically a famous equation in fracture mechanics, because it's sort of the one you think of when you're trying to conceive of what's going on at the tip of a crack. The crack opening, I think, is perhaps less exciting. But there's a particular problem that's significant in fracture mechanics, and it has the pressure distribution described between equations 316 and 317. And what you've got is that the pressure is zero out to some distance c, Latin c, from the origin. And then after that, the pressure is constant. So near the tip, you've got a constant opening pressure, and in the middle, you've got no pressure. And if you struggle through putting that distribution into the above solutions given by 313 and 314, and I actually did this myself because I just couldn't believe it was this simple, but it is. And equation 317 gives the result. So you can see now the ratio C over A creeps into the game. And this isn't, of course, the only problem that's been solved. There's a book that has nothing but solutions of these kind of problems with singularities, and it's a handbook, and I think you can find it in any engineering office that's doing anything serious about fracture mechanics. Okay, so now we need to try to cross this bridge to the case where we have some plasticity in the problem. And that's on the next slide that starts with the fracture of ductile materials. And people have fiddled with this. Eshelby is a person who made some significant contributions. The real recognition, I believe, has gone to Jim Rice. And as I say, he's championed this right through the whole period of the development of fracture mechanics. So here's what happens. People at that time really were not that adept at doing these sort of things with computers. So there was an attempt made to try to simplify the theory. Now, after all the bad things we said about some of the early workers in plasticity and them using kind of a nonlinear elastic formulation instead of what's usually called the flow rule, that the one that Prager pushed, and is no doubt the correct one. They went back and said, well, what the heck? Let's assume that at the crack tip that we have a case of loading that can be represented with a make-believe elasticity. Really, in order to have that, your stresses should all be increasing, proportionally, and you must never unload. A few things like that. But if you look at the tip of a crack, it's plausible, I would say, that you could get away with that. Furthermore, a fellow named Bernard Budiansky had shown that there are many cases where you can get away with that kind of approximation. So, armed with all of that, people then cooked up an equation like 4-1. So, in regular elasticity, the stress-strain equation can be written in terms of the partial derivative of the strain energy with respect to the strain, and that'll give you the stress. And that's a quick way to get the stress-strain equations if you happen to know the expression for the strain energy function. Well, what's been done here is they say, well, okay, now we're going to make this nonlinear, and we're going to make the curve bend over, just like a plasticity curve. If you do that, then this opens up a lot of doors, and one of the things that's you find everywhere is the use of the so-called J integral, and this J integral is a big deal. And as I've indicated, Jim Rice normally gets the credit for this. I think properly so. But it's a funny-looking integral. It's 4-2. So what you do is you have a crack, and now we're going to make a contour integration. And it's going to go from one point on the crack to another point on the crack. And in the course of doing that, it's going to enclose the singularity that's at the tip of the crack. So it's a special kind of contour integration. And on this integral, there's a capital gamma to indicate that it's around a certain curve. This has nothing to do with the capital gamma that's the energy release rate. So this kind of thing is always happening. So you have to take this contour integration, and the normal pointing outward is n, unit normal, and x is the axis leading to the tip of the crack. W is the strain energy function that you've chosen. Sigma is the stress on the boundary of the crack. This NJ, this NX and NJ are just two components. The last expression has a summation on both I and J. It's the indicial notation. So if you're fortunate enough to be able to evaluate this, then you've got a number, and the condition that's taken is that when this number gets to this capital gamma, then the fracture propagates. So to me, this is a huge jump from the point of view of physics, in that the same condition is being used for the advance of an elastic controlled crack and one that has plastic deformation. If you think about it, in a brittle fracture, almost all the deformation occurs right at the fracture. If you look at some of these pipes that they blow up, I was saying that I gave you some limit loads for pipes. I got involved in a lot of blowing up of pipes, mainly watching and measuring, and you get significant thinning of the wall section at the location of the fracture. There's a lot of things going on there, and it takes a believer to be able to jump and make this change. But it's done, and the argument, I would say, for it is that you got to do something, because people are sitting around trying to figure out what to do with materials that have cracks in them. It's a very important problem, and this is about the best thing that's around. So, and they're working on it, of course. This is a work in progress. So you then take the notion of, okay, I'm going to run around calculating J integrals. Well, these days you can calculate a J integral using one of these finite element programs, Abacus or Mark or any of these. Just do it. So you can get these things more easily than you used to be able to. But we'll fight our way through at least one of these and see what happens. Now, the J1, from what we've already seen, is related to the Ks, and what is done is that there's a relationship given between J and K that really is fudging a bit, and we'll always try to distinguish what we're talking about here. But the relation between J and K for a linear elastic plane strain solution is given as that that Ji bar in equation 4.4. And then rather than call it K1, it's called K1 material from 4.4, so that your equation relating this gamma and K1 material is given in 4.5. So this is a little bit screwy, and I want to pretty much leave it there and come back to it when we see how this is actually used in these failure diagrams. Okay, the next slide is the beginning of where we're going to try to get some mileage out of that original crack solution with the funny load on the inside. The solution is usually accredited to Dugdale-Barenblatt, but like all these things, everybody is working on the stuff at the same time, and I think you can find people who will argue with you about that, but I really don't know enough to be making any comments. So I'm going to call it the Dugdale-Barenblatt solution. So what they did is they pulled a trick, and they did a very, in my opinion, very reasonable sort of trick. And you start with the picture of, the only picture on this slide. And what they've done is they said, okie doke, we have a crack. The length of the crack is A. It's always been A in all these equations up to now, and it's still A. But when you get to A, where you had that singularity before, they say, let's stick in the yield point stress. And we'll put that uniform yield point stress from A out to A plus S. So S is the extension, if you like. And so what are we doing here? We're saying, well, the crack isn't open, but we pulled so hard on it and the singularity tried to develop, and as a result all it could do is go to the yield point. And that's because they're looking or thinking of a perfectly plastic material. When I have seen this, I've had the impression that, gee, I think if I would have done this, I would have used the ultimate strength. But as it turns out, in the codes, they use something in between. So it's a sort of a compromise. Nevertheless, you've got two regions of constant stress applied at the tips of the crack, and they are holding the crack closed desperately because they're at the yield point. What they do now is they figure out what value of S it would take to make the singularity at the tip A, x equals A. What value of S would it take to make the value of the singularity at the tip of the crack 0? I like that, because what that will do, turns out what it will do, is it makes the crack, instead of having this elliptical shape, it actually has what's called a cusp at A. And that is, it opens up with a zero tangent and not a continuously turning tangent. So they've done that, and they've used the solution that Victor Dunievsky gave me to sort this out. And they can then relate the S to the A. And if you look at equation 5.3, that gives the value of S that's needed to make the K1 at x equals A equal to 0. And you can see it depends on the far field stress, the sigma infinity, pulling way away, and the yield stress. It's got that ratio in there. And then that's related to S over A. So that's something that is used all over the place. Furthermore, this is a result that is, I won't say unexpected, but it's sometimes a little surprising. Sometimes when I think about it, I'm a little bothered. Anyway, if you look at the opening of a crack, you can calculate what's called the crack tip opening displacement. Okay, that is, if you look at the figure up there, this is 2 times the value of the y displacement at x equals a. So supposing you could get in there with a microscope and look at the tip of the crack, when you saw the end of the crack, you would, according to this solution, you wouldn't see things close. You would see a finite gap, and that's the crack tip opening displacement. It turns out that this keeps popping up, and finally it pops up so many times that you really start to believe that this is the way things are. And in fact, they make measurements of this as part of getting properties sometimes. So they can take this solution now, and they can find the J integral for this solution, you see. So what we've done is we've got an elasticity solution, and we've rigged it to put in a little plasticity. And we're going to take that now, that solution, and we're going to use the definition of the J integral to find out from the Dugdale-Barenblatt model what we should be calling the J integral. And that's what we would then set equal to this energy release rate parameter that determines when fracture will occur. So on the next slide, we go through this, or the slide goes through the derivation. I just want to mention a couple of things that ought to make it easy to understand it. And if you do that, then the whole thing just falls into place. Recall that this J integral had, it was a contour integration, and had 2 terms. One was this W, this strain energy function, and let's talk about that term first. The contour that we're going to take, and we're free to take any old contour we like, we're going to take a contour that includes the loading on the surface of the crack. So we're starting inside the place where we put these phony plastic stresses. We're going to go from there along the crack, right at the edge of the crack, and get to the end, and then come back, get past the plastic loading again, and stop. And that's going to be our contour. And when we do that, you have to imagine that you can make that contour as close to the boundary of the crack as you want. And so you just put it right at the crack. And that means there's no real area there, and consequently there's no strain energy. So you lose that term. Then the second part of the expression was this sigma ij nj partial of ui with respect to x. And the only stress you have there is this normal stress that we've put on there, sigma y. Now, that doesn't mean that's really what's there, but this is the model. So on the model, all we've got is one stress. So it's constant along the boundary. So we just pull it outside the integral, and the rest of the integration is pretty simple. And you can see how that falls out in the next equation. And then, sure enough, when you evaluate this thing, what you get is sigma y times the crack tip opening displacement. So you can't escape it. You know, it just keeps coming back. When you use the expressions for the crack tip opening displacement, then you get this equation 5.6. Now, this result is a very significant result if you look at what people do. This is, if you like, it's the core solution on which a lot of this failure diagram stuff is based. So what you would do is you would take your J integral as evaluated there, set it equal to the energy release rate, and you come then to equation 5.8. And equation 5.8 relates a property gamma, this energy release rate, to the stresses you're applying, the sigma y, and then the, I'm sorry, that's the yield point. It relates it to the sigma infinity. So given sigma infinity, you could calculate what value of gamma you would need to keep the crack from propagating. You know, another way to do it, of course, is to say, I've measured gamma, I know what gamma is, now I'm going to find out what sigma infinity I can apply. And that's really the key to this failure diagram business. So the next page, our slide, gives a plot of this, and it's kind of an interesting plot. You've got a ratio here. Let's see. That ratio is a calculated value to a measured value, and it starts at 1 when the far field stress is very low. So you can go very low on this because you have a singularity, and no matter how low the stress gets at the tip of the crack, you would have a singularity. But you can see that the amount, this ordinate here, is telling you how much how much of the material property you can use. And when you start out, you might as well just use brittle theory, because this thing is almost 1. When you get over to this far field stress over the yield point of about 0.6, it's still 0.9. So the influence of a flaw is not being felt. And let me point out that the elastic stress intensity factor is dependent on the length of the crack. So this is a case where you've gone out and looked at your material, x-rayed it, and do whatever you need to figure out your maximum crack length. If you know that, then you can get your elastic stress intensity factor, and then you know where you are on this curve. And you can see as you approach, as the far field stress approaches the yield point, this curve takes a dive. Okay, and it's all near the end. So I think that's kind of interesting. I tried to put in here, if you like, a practical example. L80 is a material that's used pretty extensively in the oil industry And one reason I chose it is that of the ductile materials used in drill pipe and casing and such, it's got about the closest thing to a perfectly plastic material. That is, it goes up and it yields and it just keeps on straining at essentially the same stress. L80 means that the minimum guaranteed yield point is 80, but in every case I've ever seen, for the scheme that they use for materials, steels used in the oil industry, the yield point always is much greater. See, this is guaranteed to be 80 KSI, and you can see when you go to measure it, you get closer to 100 KSI. And these are numbers taken off of averages for a lot of different samples. And then this gamma, which had to be measured. And I have to say a few words about that because this is not an easy number to get. It involves some pretty tricky technique, and it's very expensive. So these numbers are, just not everywhere. And then Young's modulus, of course, is 30. So for this, and let's see, somewhere I thought I chose a... Oh, okay, I worked it the other way around. Okay, yeah, I took a value of this energy release rate, which is really taken off of the preceding curve on the preceding slide, and I just pulled out a number of 3, and that gave me a far field stress of about 0.97 of the yield stress. If I do that and then turn this around and solve for the crack length, I get about 1/4 of an inch. So that's the kind of stuff that you're looking at, is cracks the order of that length. Awfully hard to find those cracks. When they do their inspection, the most likely thing that they're going to pick up is where perhaps the inside of the tubular has been gouged, and they'll get a little streak in there that they treat as a fracture, and that's about as far as they've gotten on all this stuff. But I'm sure that they'll figure out better ways to do this as they go. Anyway, if you know anything about your flaws, you know your material properties, then this curve, which is really based on the Dugdale-Barenblatt solution, is going to tell you, it's going to relate the size of the cracks and the stresses that you can apply to the material. Now, that curve existed for a while, but since it was since all of these standards are written as a committee, things never get left the way they start. So a number of things have happened to modify that curve. Okay. Well, first off, and going to the next slide now, we're getting to what is called level 2 failure assessment diagram. What they do, and this makes sense, is they take this Dugdale-Barenblatt curve and they put a rectangle inside, because it's real easy to calculate those numbers. And if your stress point and load point is going to be within that rectangle, then you pass level 1. So that, what that really means is the load is so low that there's nothing to worry about. So level 2, they actually use these criteria, or the criterion from the Dugdale-Barenblatt curve. And this, there's several codes out there, and one of these is PD 6493. It came out in 1991, and they did a few things, and you can see here that instead of using the yield stress or the ultimate stress, as I would have probably done, they take the mean of the two. That was done by committee. Some people arguing for one side, some for the other. And I think everybody threw up their hands and said, okay, let's split the difference. It's an empirical decision. It's a committee decision. Then if you rewrite everything and put for your ratio, instead of sigma infinity over the sigma of the yield point, call that SR, then you get on equation 6.3 what I'm calling the KR. KR, if you remember, is that's that ratio of the two Ks, one calculated, one measured. This is the equation they use. Then they got into some other things, and I think for good reasons. And the main thing was that General Electric Company, who of course is very heavily involved in nuclear power, and this stuff got really funded a lot by the interest in nuclear power, because that's a fairly brittle material that all this reactor is enclosed in. It's pretty strong, but it's not real brittle, but it's a little brittle. And General Electric funded the Electric Power Research Institute in California to use some computer models, because by that time, you see, you're getting close to 1996 now. People were figuring out how to do all this stuff on computers, and they worked out a lot of curves, and they did this using a nonlinear elastic equation, which is given at the bottom of the page. It's called the Ramberg-Osgood stress-strain equation. And if you look at that equation, you have epsilon over a reference strain. I'll tell you what that is later. And then you have the stress over a reference stress. And then you have the ratio of the stress to the reference stress to the n. N is going to be a big number. It goes up to about 20 on some materials. And that just goes up and takes off at your yield point. So epsilon's the strain, sigma's the stress, sigma 0, alpha, and n are constants that you cook up in Anderson's book, is pictures like the inserts on this curve for all kinds of loads and combinations, and then that book that gives the stress intensity factors has just got tons of that stuff. In the long run, this fellow Ainsworth really, as far as I've been able to tell, he did a lot of curve matching type of work, and he worked out equations, and it's shown in the lower of the two curves, the kind of stuff that he's worked out, and that have really become now part of the standard. And the bottom equation on this is the so-called Ainsworth's model. So for the design stuff that's around, they use Ainsworth's result. And of course, this is important if you're designing these things and you have to convince an insurance company or anybody else that what you've done is legit. If you follow the code that people write, then you're sort of protected. And Ainsworth's model is what's in the code, and that's what people do. Okay, on the next page, there's a plot of what I've labeled here, Ainsworth FAD curve, failure assessment diagram curve. And this is what's used, and for this L sub R, different codes. There's more than one outfit. API is in this game too. The number of their code is 579. So sometimes this LR is used as the abscissa and sometimes SR, and that's a matter of whether or not you're using the yield point or this so-called flow stress, which doesn't mean anything except it's the average of the ultimate and the yield. Now, the next slide is taken from API 579, and this is what people have to try to live with when they're trying to design things. And you can see now that more people have gotten their finger in the pie on these committees, so things are pretty chopped up, it looks like. Okay, but this picture is the failure assessment diagram for this API 579, and they're always changing it, so they possibly have some slight changes, but nothing I've heard about that's exciting. I mentioned to you that there was this level 1 assessment. Well, if you can get into that little rectangle at the lower left of the figure where it says acceptable region, you don't have to think about or do anything. You're okay. If you don't make it, then you go to the Ainsworth curve. But you can see various people did have some feelings about this, and I presume they're honest people trying to get it right. So they talk about steels with a yield plateau. I think what they mean is it doesn't harden much. And then they've got cutoffs for various kinds of things. For carbon manganese steels, they get cut off. Stainless steels get cut off at some point. But there it is. That's what you got to do. And this equation 9.46 is basically Ainsworth's equation. And then you can see there's a little fudging going on here according to what kind of material you have and how you put it into this equation of theirs. Okay, I think that's all I can say about the failure assessment diagram. If you get into this and you start designing, you simply have to use this sort of stuff. And my own observation is that fracture mechanics, being a fairly young endeavor, technically, has caught a lot of people who 50 years ago I would have called them metallurgists, but then they became material scientists. But this stuff has come up fairly recently. So if you get an old-timer, many of them, many know exactly what they're doing, of course, but I've had occasion to run across some that really don't understand this even to the depth that I've explained it today. And you have to be very careful when you listen to advice from people, because not everybody really digs what's going on here. Got a bunch of references that you might enjoy. The second to last reference there, number 11, is a Welding Research Council bulletin. There are about 3 of those that are really very good. They're very good, and you can see that this Ted Anderson was instrumental in putting those together. So a lot of what's in those Welding Research Council bulletins appears in Anderson's book, and that's the place to look to see what's happening, and looking at their more recent things would be an indication of what's going on. Okay, now we've talked a lot about what fracture mechanics is and how it's implemented, but not so much how things are measured. There's several ways of measuring this, but the real problem, and it still exists, is that when you run these tests, if you have a brittle material, it's straightforward. You follow the ASTM rules and everything will work out okay. But that's not what the oil industry has. And as a result, you run a test and you make a bunch of measurements, but when the test is over, you have to go back and check a bunch of things. And these are things you don't know before the test starts. So you can run the test, and then you go and check these things, and you find out it's not a valid test. This is very discouraging, because these tests are not cheap, and it can get to be a problem. So it's still a problem that way. It's hard to get good results. There are a number of labs in the country where you can send your samples. Now, they can give you a number, and they'll always tell you, yes, it passed all the criteria. But if it didn't, and you're trying to get something certified somehow, then you're in the soup. You're going to have to do something about that. And there's things you can do, but it's just not as easy. It's certainly not a tension test. It's a lot more than that. The I think it's probably the most popular, but also the easiest to understand, and that's why I'm talking about it here, is what's called the double cantilever beam specimen, sometimes called DCB specimens, because the oil industry has the habit of doing that. Most industries do, really. So what you have here is a rectangular bar. It's a lowercase t thick. It's got, this isn't really the crack, it's got a sawed slice in it of length. I'm saying A because it is where the crack would start. H is the half height, and you pull it apart. Okay, and now you want to get the properties of what's going on. Now, the underlying equation for this is remarkably simple, and it's one of the things that shows what a bright guy Jim Rice is. He looks at this and he says, looky here, this is just 2 beams. I'm pulling them apart and they're attached back here at A. So I'm just going to use beam theory, and I'm going to calculate the work that gets done, and I'm going to calculate then, if the crack extends, what the energy change would be. So when I get to the point where the crack does extend, I'll know my load, I'll know A, and therefore I can use equation 1, I can get my gamma, and it's based on totally elastic theory. And that was the first thing that was out, and this was used as long as the elastic theory was thought to be good. However, what was subsequently done is this, I call it a Dugdale-Barenblatt type approximation for this double cantilever beam. So you pull the same trick here that Dugdale and Barenblatt did, and you put a little plastic region at the tip and work the problem as is indicated on the next slide. And this is the section that says analysis without shear deflection or base rotation. Okay, so we need to talk about that, but before, what are you going to do about this crack? Because you've cut a slice. They use very thin saws to cut that groove in there to a depth A. But that's still not a crack. That's not good enough. The standards tell you what to do on this. I guess they've learned through hard experience that they give you a way to determine some cycles to apply before you start the test. And those cycles are enough to start a real crack from the tip, but not cause the whole thing to break through. So you have to go through this, and that makes the test more expensive, but you got to do it. And then once you get the crack started, there's this solution. This is Dugdale-Barenblatt type, and it's got a picture analogous to the one we had for the ellipsoidal crack. And as before, we've got a plastic region that extends for a distance lambda in this figure. And you see I've only got half of the beam here because of symmetry. It's just like it's built in past A on each side. So I want to figure out what the Dugdale-Barenblatt type solution for this works out to be. And you follow pretty much the same scheme. And what I've done is I've put in the part of the solution that's just beam theory. On the next slide, if you're a mechanical or a civil engineer, these equations should be so obvious to you that it's almost laughable. So what you're doing here is you're solving for this cantilever beam in the previous slide. You're looking at the region on the beam from the tip where the load is applied to the depth of the sawed crack, or actually it should be the real crack that's slightly extended beyond A. And then beyond that, the plastic region, lambda. So you apply the load P and do a plain vanilla beam theory solution, as though that was a built-in beam with load P. Then you turn around and for the loading with the yield point load, you solve that flat out as a beam problem. And you're able, by getting the energy, to then determine the value of gamma, which is the rate of change of the strain energy with respect to this extended region. So you set the two yield point, conditions for the gammas equal to one another. And you come up now with a solution. Well, first with an equation 4 on this page. And you can see you have a quadratic equation in lambda. The one you want, of course, is the smaller root. And it has to be the smaller real root. And positive root, I'm sorry. So we get the positive root from that equation. And knowing what it is, we can find virtually everything else because we've done these beam solutions before. So what is being done here is we're using those equations to calculate, after we've got lambda, to calculate the crack tip opening displacement. That would be the displacement where the crack ends, but not into the region that's lambda long. When we do that, with this crack tip opening displacement defined the way it always is, we get equation 6, and then we say that this energy release rate for that material, if the crack advanced and these loads were present, then you take sigma y times the crack tip opening displacement, and you have the energy release rate, which is given on the next slide. And if you want to try to make a FAD diagram, you can do that and follow pretty much the same rules as was done before. If you go then to the next, you can get what's labeled here, FAD curve for the DCB test. So, failure assessment diagram for the double cantilever beam test. You've probably noticed that I've been careful to say, I hope I've been careful to say, that it includes the beam bending. We saw that, we worked that out. No shear deflection, no base rotation, no grooves. There's an interesting side story that goes with that. If you've done much beam kind of analysis, particularly when you get to a short beam, you're likely to want to throw in what's called the shear deflection. So a couple of different ways to do it, but the simplest way would be to take the load in this prior problem, take the cross-section of of one of the two beams, and take that load divided, the load P divided by that cross-sectional area, and throw in a shear strain. Okay? If you do that using the usual beam theory, you get just nonsense when you try to go through this analysis that I just went through. And why is that? The why is that is that if you include the shear deflection with the other restrictions of the problem, the crack doesn't open as a cusp as it should with the Dugdale-Barenblatt solution. It opens with an angle. So that won't work. So what can you do? Well, one way out of this is you can look at the region near the tip of the crack, and you can work a little elasticity problem that puts in rotational resistance for the sample, the test sample, beyond the crack. So you put in a little elasticity back there, and it's not too important how you do it. You got to get a reasonable answer, but it's a relatively straightforward elasticity problem to get an approximation to. If you do that, then you can include what I'm calling the base rotation with the shear deflections, and you get something real nice. And it's an improvement over the solution that only includes bending. Another thing that's done is that on these samples, it's not indicated on anything here, but where you cut with a saw, you frequently cut a groove in each side. And that's because, life being what it is, sometimes when you pull on these samples, the fracture doesn't progress just straight ahead. It pops off to the side, and you break off one of the beams, and that ruins the test, and nobody likes that. So they put a groove in frequently, and that's really no new complication. The only thing that changes there is the area of the fractured material. So that's easy to do, but I'm not doing it here. And there's several curves showing different things. There's the Fed curve, then under that is the J integral. And for that one, I've used some typical properties. A yield stress of 100,000 psi, that was like the L80 that we looked at just now. The next three are dimensions of the standard dimensions. And you know, when they do that on a standard, that's sometimes an indication that if you change the size of the specimen, you might change the result. And that's kind of true here. So they have a standard size, and of course, Young's modulus, you take what you get. Then on the next page, instead of the J integral, there's a stress intensity factor given. And then there's a curve. This gives lambda. So there's a lot of curves here. And in one way or another, you can use these curves sometimes to check a sample to see if everything is the way you thought it was going to be. And that's about all I have to say about the sample testing, except that when you have a ductile material, you must be prepared for a certain amount of disappointment in the results, because the test turns out after the fact to not be valid. A brief comment or two here concerning fatigue of materials and how fracture mechanics can play a role in that. I think most people are aware of usually called the Goodman diagram, and then like all these things, there are some other names that sometimes get mixed in. But in the Goodman diagram, you plot a number of cycles to failure on the x-axis and the stress on the y-axis, and then you put some boundaries in as to how big the stress can be if you intend to have the material used for a certain number of cycles. And that's an area where you hear it said that that this is a place where fracture mechanics should shine. And it does okay. I'm not saying that it doesn't, but what the notion is that in fatigue, if you think about bending a bar back and forth until it breaks, you in the course of cycling, you get intense strain hardening at the tip. And a strain hardened material looks a little more like a brittle material than a ductile material. So there's great expectations when you try to apply fatigue failure based on fracture mechanics. On this curve that says comments concerning fatigue failure based on fracture mechanics. There's a little curve there. It's a typical curve. It came from Anderson's book. And what they're trying to show there is that there's a couple of parameters. They're trying to show that the rate of growth of the crack length, so that's how it's propagating, is measured in terms of the increment in change in length divided by the increment in the number of cycles. And it's written as DADN. And for some reason, people in fatigue always plot everything with a log coordinate. They take the log of the parameter. I've often suspected that if you keep taking the log enough, you can get a straight line. And maybe that's some of the unconscious motivation for this. Nevertheless, they plot this log of DADN versus the log of what they call delta K. The K is the old stress intensity factor. And the delta K is how much you're cycling. So K is going from K1 to K2. And of course, the wider the spread there, the faster the crack is going to grow. And so that's why the curve generally has a positive slope. You know that there's, at least for steels, there's what do they call it, a fatigue limit or something. It's the stress below which you get no fatigue fracture. And that's called threshold by these people. And then, of course, when you get to a certain point, the growth rate just takes off. So if log of delta K gets big enough, the party's over. In the meantime, in between, there's a straight line section. And various people have determined this experimentally and tried to make some sense of it. On the next page, there's a little sketch also swiped from Anderson showing the variation in the K and this notion of an elastic singularity zone, but the work hardening as you go along leaves this so-called plastic wake, and they're aware of all of this. And the parameters that they use is Kmax and Kmin, and that's a little different than you normally use in something like a Goodman diagram. But the delta K is just the plain difference between the extreme values of K, and R is a ratio of the two. So R is related to the mean value of K, which is given on the line below. And the assumption here then is that dAdN is a function of delta K, the difference of the extremes, and R, which is a measure of the mean. This sounds a lot like the Goodman diagram, the kind of way the parameters are put together. Now, this next curve just says if you know dAdN, you start with a certain crack A0, and you've got some limit that you want to go to. You may have determined that that this length is where that crack is really going to take off just from the static loads. So you take your integral from where you start, these would be the intrinsic cracks in the material, up to the limit that you can live with. And if you can know what this dAdN is, you can make that integration and find out how many cycles you should expect this sample to resist the loads. You get into problems, of course, like taking into account the past history and all that. That's all done pretty much the same way that it's always been done. The result of all this, though, is to thinking back to that previous curve, where the log of dAdn versus delta k, log of delta k. That straight line section is characterized by this equation here. dAdn is c times delta k to the m. Okay, so it points out here that in the earlier stuff they thought m would be about 4, and sometimes now they think it's maybe closer to 2. So like anything in fatigue, if you just plot the raw data, it looks like you've fired a shotgun at the curve, because it's so much scatter. So what Paris has come up with, and the fellow that did it with him is Erdogan. And I tried to pronounce this man's name in front of Prager once. And Prager, who I've mentioned lived in Turkey for a while, he said, "Paul, never try to pronounce this man's name, because you will never get it right." So you see it written there, and that's his name. And he and Paris were the ones that cooked up this law. Okay, the things that can goof up results is if your loading is such that the crack closes. Obviously, when the crack closes, it's not going to propagate. Sometimes when you have something like action with hydrogen sulfide or something in the atmosphere, you will form a deposit on the face of the crack, and that's usually some kind of corrosion that's going on, and that tends to, well, chemically it goofs up the material too, but it also gets crud in the crack, and keeps you from getting anything too perfect. People try to explain the existence of a threshold stress, but they've been doing that forever, so that's nothing new. The minor criterion is used, and that's just the most obvious linear combination of prior damage. And what it comes down to is when you get into a special area of fatigue called low cycle fatigue, you're talking now thousands of cycles, not millions of cycles, it appears that you're still better off using Lukoff and Manson's formulation, where you're saying that the allowable plastic strain amplitude is the strain to cause failure in one cycle times the number of cycles to the power C that you want to go to, and then you struggle to measure C, and it's between minus 0.5 and minus 0.7. Well, that's not much, but I wanted to at least mention the existence of fatigue and how people have looked at it or tried to look at it in the case of fracture mechanics, because there's undoubtedly some good stuff there, and I'm sure that that kind of effort will continue. Well, you probably noticed that we're picking up some odds and ends here concerning, well, right now fracture mechanics, but that's of course tied into plasticity, and there's been so much effort in fracture mechanics in so many different directions that I wanted to try to touch as much as I could in the time that we were going to have. So I'm going to call your attention to a bunch of pages, but I'm not going to really do much other than just call it to your attention. Most of these are found as appendices in that stress intensity factor handbook. Some of the stuff is coming out of Ted Anderson's book. But there's some things that we've mentioned casually that you can prove, and if you're interested in that sort of thing, I've got a bunch of that stuff collected here, and it goes on for quite a few pages. So this first thing about the relation of the elastic energy release rate to the strain energy, that's something we actually used, and I tried to slip by you on the DCB calculation, the analysis there. But this first case, where this is the first thing in the appendix, some fracture mechanics considerations. This is showing that if you just take any kind of a body, I draw it as a potato-looking cloud, and have a crack, length lambda, and I'm trying to look at how the strain energy changes with the load. And that's done in some books. A lot of this is done using a compliance. And compliance being the displacement per unit force, or the reciprocal of the stiffness, if you like to think of it that way. And you can relate the value of the energy release rate to how the strain energy is changing, the U being the strain energy. And you end up at the end with this capital G. Remember I told you that capital gamma was going to change to capital G. Well, this is where it happens. And there's a little a curve demonstrating how, as the crack length changes, the slope of the response curve, the P versus delta, changes, and that the area between the two is divided by the change in crack length is related to the energy release rate. So if you like to look at derivations and listen to stories, that's good. It obviously is, what I just said is not going to apply to a plastic material. Then there's this business of the elastic stress intensity factor, how it's related to the energy release rate. And here there's a number of things. The details of the stresses around the singularities are given here. Oh, let's see if I can identify. If you go to the case where we have three little figures at the top of the page, this is that mode 1, mode 2, mode 3 that I mentioned earlier. I was doing that with my hands, and now we have a real picture that does it. And everything, as I said before, we're talking about has to do with mode 1, because if you've got mode 1 under control, you can do the others. And this is under that picture of mode 1, mode 2, mode 3. There's a little quickie proof that G is related to the K1 squared over E. If we continue, there's a section called the J integral and its path independence. And I said it was path independence. If you don't choose to believe that, you can go through this derivation, and it's actually not bad. I looked at several derivations. This is the one I like the best. It seemed the least painful. And as I recall, this is the one that's in the paper published by Rice and Drucker. So it's a very nice proof. The next little section is on the equivalence of the J integral and the energy release rate. And once more, it's a derivation. Lots of summation signs and derivatives and so on. And this is now the last of these add-on things. And it's the relation between the crack tip opening displacement and the J integral for the Dugdale-Barenblatt approximation. This is just a little more detail on what was gone over very quickly when we were going through the Dugdale-Barenblatt derivation. This is for the people that maybe want to dig a little deeper. That's what these added parts are. So I am I'm really done with the plasticity and the fracture mechanics. But if you've got a good ear, you probably have detected that I have a Louisiana dialect. And I am from Louisiana. In fact, I'm from New Orleans. And there, it's always common whenever you buy something, you get something that's like a baker's dozen, 13 rolls, and it's called lagniappe. So I thought it was only proper that I would include some lagniappe. And I want to make a few things. I want to straighten out some things here that I've used pretty loosely in the discussion, and things that are pretty loosely used in general, particularly in engineering circles.